Hello guys, so this video introduces the 7.2 forces assignment, and the first video will cover essentially an introduction to forces, or kinetics is probably the correct term. So this video will cover a few small aspects of force before it leads into the next video, which looks more in depth at Newton's 3 laws of motion. So this is just an overview really. We're going to look at what force is, how we would describe or define force. We'll look at how we use arrows and diagrams to represent the different forces that might be acting on any object. Look at a few different types of forces, and then look at the how forces almost act against each other and whether they're balanced or unbalanced. And then finally the 5 effects of force. So, what is force? We probably have a good sense of what it is without maybe being able to define it. But essentially for our course we need to understand it as a push or pull exerted on a body that tends to change its state of motion. So this will align with Newton's first law in terms of motion and changing motion, but essentially forces or pushes or pulls. And of course the object might be a human body, or it might be a bit of sporting equipment. We measure force in newtons, and of course the letter is a capital N, and essentially 1 Newton is the force that's required to accelerate an object with a mass of 1 kilogram by a velocity of 1 meter per second. So 1 Newton is the force that you'd use to accelerate a 1 kilogram object by 1 meters per second. Of course, it's proportional. So if 2 Newtons was applied to any object, it would accelerate twice as fast. And the other thing to bear in mind is forces are vectors. That means we have a sort of a magnitude, how much force is there, but also we should really account for the direction any force is applied, because that totally makes sense when you look at a lot of our sports. So for example, if this hockey player applied a force in a particular direction, the ball would go off in that direction. If they applied a force to the ball in a different direction, it would go off in a different direction. And of course, the other factor, of course, is how much force is applied. So if they push harder and apply a bigger force, the ball will accelerate away proportionally to that amount of force. That will come out again in Newton's laws. So forces are vectors, how much force is being applied, pull or push, and in what direction. And it's measured in newtons. Just a sense of what types of forces we have. So these are probably, there are lots more than these, but these are the ones that are most likely going to be relevant to us within this course in sport and exercise science. So forces that are applied externally, forces that are internal, which are your muscular forces. We obviously do this all the time. We apply forces through the tendons which pull on the bones which allow us to move. Friction force between 2 objects. Air resistance, so we'll look at that in one of the later videos. This is sometimes called drag, so it can be drag as a resistance force in the air, but in water it's called drag. It's the force that opposes motion. And again, we should already be aware of gravitational force, 9.81. So objects accelerate 9.81 meters per second towards the sort of core of the Earth, really. What you will need to be good at, and when you explain this topic or this introduction in terms of the types of forces, you'll need to give examples of them. So again, they are present in lots and lots of sporting actions, and it's just for you to pick out them and give them simple examples as part of this introduction. So friction force goes so that the shoe, if it was a smooth sole, would flip that way. So we have a tread on the bottom of our shoe to create friction, and friction is always going in the direction of motion. Okay, so we stop ourselves slipping by the force that pushes us that way and stops us going backwards, if you like. Air resistance has a little bit but minimal effect on a long jumper, when they're flying through the air, but gravitational force has a an important effect to push us down to the ground. We've got external contact forces. We've got the muscular internal force being applied as the boxer. The triceps extend the arm, and the contact, the applied force on the opponent's face. We've got the applied external force by the fingers on the ball, but we've also got this rotational force, and we'll actually look at rotational forces and flights a little bit more in assignment 3 when we look at angular motion. We've got an applied force with the table tennis player applying to the table tennis ball, of course. And again, we've got a pull force. So we've got to overcome inertia of these weights and gravity pushing these weights down. And we pull on this bar to pull on the lever system to try and pull the weights up to overcome inertia and change those weights' motion. So lots of simple examples. You guys need to find out your own examples to give for these types of forces. Now, diagrams are used often to represent forces. And remember, forces are vectors, so we need to show how big a force is and what direction a force is being applied in. So, actually, I think it's the third one. Yeah, here we are. So this ball is being struck. The length of the arrow describes or represents how much force is being applied, and obviously the direction of the arrow is the direction it's being applied in. In this example, the athlete's weight, which is a vertical force, always starts at the center of mass and always goes vertically downwards. So remember, weight is mass times gravity, and the length of this arrow would represent this athlete's weight. So if this athlete was bigger and had a bigger weight, this arrow would be a bit longer. If they were leaner or smaller, this arrow would be a bit shorter. We've got friction force in this diagram. So the studs are stopping this athlete slipping that way, and the friction force is working in the direction of motion. We've also got these reaction forces. So we've got our weight pulling us down, and where we've got contact with the ground, we've got equal and opposite arrows working upwards vertically, and these are called reaction force. So these are equal and opposite to the weight force. And you can see that there's two arrows for reaction force, and that's because there's 2 points of contact, and these two added up equal this one downward weight arrow. If this athlete happened to be on one foot at the time, there would just be one reaction arrow, which would be the same length as their weight one. This is how we might represent different forces acting on any object too. So we've got 1, 2, 3 forces we've identified in this example, one on this one. On this golf ball example, the ball's been struck in that direction of the red arrow. It's got, because it's spinning, there is a lift force, which we'll learn a bit more about in assignment 3. Gravity, of course, this arrow technically should start in the center of mass, which is in the middle, so it should really start from there. And we've got this drag force, this air resistance force, which is working against the direction of motion, kind of slowing it down a bit. So again, just showing how these arrows can represent forces on objects or athletes. Now, free body diagrams should be titled actually, but I've omitted that from these are called free body diagrams. And this table is not something I'm going to go through and explain. You can pause the video and have a look at it. But it essentially describes the main 4 free body diagram forces that need to be represented. And you're going to, in your introduction, choose one sporting example and use this information to draw a free body diagram. So this top diagram actually has just the vertical forces. It shows weight and reaction force. We've already talked about those. Excuse me. So these columns here describe how to draw those appropriately. This diagram just shows horizontal forces. So these two are the horizontal forces. Friction in the motion direction and air resistance in the opposite direction. And again, this describes how to draw those appropriately and how to represent them. And you need to do that. So there's some examples here. Again, I'm not going to go through them one by one. I'll show you the answers. You need to find your own examples of them. So we've got different sporting examples, and here are the answers to that. So we've got weight. Weight is exceptionally long here because we're not just talking about the weight of the athlete, we've got this barbell to account for it as well. And we've got the 2 points of contact, and we've got the upward or reaction forces. We've got weight work downwards here. We've got the vertical reaction force, which is the same from the point of contact. We've got air resistance, which wouldn't be particularly significant with a sprinter. And we've got friction force, which, especially because of the blocks, is much larger, which makes sense really, because this being a smaller arrow, this being a bigger arrow in the direction of motion, means that this athlete's going to propel themselves forwards in an acceleration. We've got weight working downwards, we've got ground reaction forces equaling that upwards, and in this final example we've got the long jumper with weight acting downwards from their centre of mass. However, because they are in the air, there's no points of contact, so we've got no reaction force, no ground reaction force. We might have a small but negligible air resistance affecting them, but those are the only two forces that are acting on that particular athlete. So let's move on. What we need to do now is understand how forces might interact with each other or oppose each other or work against each other. And obviously, if the white team here had a bigger force applied in the direction to the right, then the red team could push back. Obviously, the motion would change. If it was the other way around, red team applied a bigger force in that direction, the white team would be pushed backwards. If the forces happen to be equal, then there would be no change in motion. Now, what we need to understand is this term net force, and that means what's the sum of the two forces? So if the sum of the two forces happens to be equal, for example, they pushed, the same force was exerted by each team, there basically would be no motion. And that would mean that the net force would be 0 newtons. Okay? So when forces that are acting in opposite directions are the same amount, same magnitude, but in opposite directions, we have a net force of 0. And as I've established already, there would be no change in motion. Now, this example happens to be a stationary example there still, but that would also be true if an object was moving. If forces acting on an object that was in motion were equal and opposite, they would maintain constant velocity. So please note that net force applies to stationary objects, stationary force, where the object is stationary, or objects that are already in motion. And a net force of 0 means there's no change in motion. So we also call this balanced net force, balanced forces. So for example here, the tug of war, they're pulling 300 newtons, they're pulling the opposite direction 300 newtons. These numbers are the same, so the net force is 0, so there would be no change in motion. They would just be pulling against each other and be still. The ball has a force acting downwards, gravity, weight, and the reaction force acting against that is equal and opposite. And if there's no other forces that are acting on this ball, the ball will just sit there. There's no change in motion. It's a balanced force upwards and downwards. This is a balanced horizontal pair of forces. This one, the windsurfer is, traveling along, so there is motion. The wind is applying a force to the sail, and the muscular force of the surfer is applying an equal and opposite force back. They will just carry on at the same velocity in the same direction. These all represent balanced forces. When you give examples in your work that are your own examples, you need to give numbers like this. Don't worry too much if they're made up numbers, that's totally fine, but you need to give numerical examples in your sports examples. So just to summarize, balanced forces is when two or more forces are in operation and they are equal size and in the opposite direction. The net force will be 0 newtons. I should have added the N on there, 0 newtons. And if we have a net force of 0 newtons, the object will not change motion, whether it's still or whether it is already moving, in which case it will keep a constant velocity. So what about if the forces are not the same number? If we've got an uneven force, or we would call this an unbalanced force. For example, if this team worked particularly hard and managed to generate bigger force, they were now pulling 400 newtons, whereas the original team only pulling 300 newtons. What that would mean is there is an unbalanced force. These forces are now not equal, and there's a bigger force in that direction. As you would understand, they would generate motion, change the motion, and they would pull, both teams would travel to the left. Similarly, if there was a gust of wind with our windsurfer, so now there's a bigger force being applied by the wind on the sail than the windsurfer, this would possibly change motion by changing direction, pulling him off the board, possibly, well, I was going to say possibly increase the velocity if he can hang on, but it would change the motion of that windsurfer, most likely change its direction. So, unbalanced forces are when a force acting in one direction is bigger than the force acting in the other direction. You might assume that this athlete might be able to generate a bigger force pushing in that direction than this person can push in this direction, and therefore they might win the arm wrestle. Where there's an unbalanced force, the object will accelerate in the direction of that bigger force. And in this example, the net force will be a number value in one direction. So if they generated 10 newtons, they generated 5 newtons, the net force would be 5 newtons in that direction. Okay, so the last thing to look at in this video is the 5 effects of force on objects. And pretty much they're predictable and straightforward, and you probably know this already, but just need to explain these in your introduction assignment or introduction to forces section. So, forces can make any object, whether it's a human or a piece of equipment, change motion. So from being stationary to becoming in motion. That makes sense? You strike a golf ball, it was still, it was stationary on the tee, you strike it, you apply a force to it, you create motion. You can change direction of objects or athletes. So if this ball is approaching the tennis racket applies a force to the ball, it can send it back in the opposite direction, changing the direction. Objects can be accelerated, so whether these are athletes running or, again, either of these examples, when you apply a force, it might be traveling at a certain velocity and you might accelerate it in a given direction, increasing its velocity dramatically. You might also decelerate objects, or objects might decelerate. So essentially forces are used to slow objects down or to slow you down. And lastly, perhaps one you might not feel is as obvious, is forces can change the shape of objects. So you can possibly see a little bit there. With the tennis ball striking the racket, the strings, I guess absorbing the force, change shape a little bit. What this video shows, and I'm not going to play the video, it shows that when you use a driver and apply a huge force to this golf ball, it actually changes its shape. If you look at boxers, I'm sure you could find examples of where boxers strike the other boxer and their face becomes contorted and changes shape. It's obviously the force, the impact has changed the shape of the object. If you strike a football or a rugby ball, they will slightly change shape as a result of that force. So those are the 5 effects of force, and that's the last example of the introduction, or the section of the introduction to forces. Obviously what you need to do is pick your own examples and make sure you can apply those 5 effects of force to your examples. It doesn't need to be one example. You can use different examples to show each of those 5 effects. So there we have it, introduction to forces, several aspects that you need to explain with your own examples using numerical values throughout.